So let us talk about the role of LUB property in real analysis. Okay. So basically, as you can see that there is a video on LUB property by Kumar sir. That the title of the video is "What Makes Real Analysis Tick," and I hope many of you have already watched that video. So in that video, Kumar sir have talked about that it is the LUB property which makes the real analysis tick. That is, if you remove the LUB property from real analysis, then whole real analysis will collapse. So basically, it says that is all the major results in real analysis we use in real analysis either directly or indirectly depend on the LUB property. So in today's talk, I want to show one proof and also discuss some examples in which the LUB property enters. And I also want to prove one theorem in continuity. So I hope you enjoy today's session with me. So let us start my talk. So this is the definition of LUB, the least upper bound, as you all know. Let A be a non-empty subset of R and bounded above in R. Then alpha belongs to R is said to be the LUB of A if and only if first alpha is an upper bound. Second, if beta is an upper bound, then alpha is less than equal to beta. So I hope all of you are already familiar with the definition of the LUB. Yeah. So this is the LUB property of R and also known as the order completeness of R. Okay. So what does it says? It says let A be a non-empty subset of R and bounded above in R. Then there exists alpha belongs to R such that alpha is equal to least upper bound of A. So basically this property or exam is the very simplest exam in real analysis that you can think of. You have a non-empty subset and it is bounded above in R. Now, what do we mean by bounded above in R? Can anyone tell me? What does it mean to say that a set is a bounded above in R? Can anyone like to say something?
If we found above, then there exists a real number alpha. Alpha is upper bound for the set.
Yeah, correct, Ram Shankar. So basically, when do we say bounded above? There exists alpha belongs to R such that given any x belongs to A, x is less than equal to alpha. Yeah. So this is what it meant to be said bounded above in R. So basically, if you have an upper bound for a set, then we can find infinitely many upper bounds, right? And among all those upper bounds, I can see a least upper bound, the smallest of all the upper bounds. That is called a least upper bound. Okay. So that is LUB property says if we have a non-empty subset of R and it is bounded above in R, then there exists a least upper bound of A. Okay. Yeah. So now I want to discuss the basic examples and theorems. So I would like you to tell me the theorems you feel like and the results you come across in real analysis in which you use the LUB property directly or indirectly. So please give me some examples. So I will start from example number 1. Yeah, please, can anyone say?
Archimedean property.
Yeah, very nice. So as you all know that Archimedean property is the simple most property that uses the LUB property, and it is the first theorem real analysis which be proved by LUB property. So someone says Archimedean property. So can anyone say what is Archimedean property?
Given any real number alpha,
Yeah,
there exists a natural number n such that n is greater than alpha.
yeah. So basically, given any alpha belongs to R, there exists n belongs to n such that n is greater than. Oh, sorry, let me just use x here. Yeah. Given any real number x belongs to R, there exists n belongs to n such that n is greater than x. So this is the Archimedean property, and it is equivalent to saying that n is not bounded above in R, right? So this is equivalent to saying that n is not bounded above in R. We have just expressed this statement in terms of the quantifiers. So this is the Archimedean property, and I hope all of you know the proof of this property. Yeah, because in when we went to the MTTS, this is the first property which we taught by the professors there. That is the Archimedean property, and it is the and it is the single most property that actually uh, make me appreciate the LUB property very much. So it is from the MTTS camp itself. Yeah. So I want to talk about example number 2. So can you talk about? Can you give me next example? You feel like any other theorem? You feel like which uses the LUB property directly or
Greatest
indirectly?
integer function. Greatest integer function.
Yeah, greatest integer function. Yeah, greatest integer function. So what does it say basically? Dhruv, can you tell me?
Given, given any real number alpha, there
Hmm.
exists integer z such that z is less than equal to alpha is less than z plus 1.
Yeah. So basically, what does it say is given any real number belongs to R, there exist. I'm using the M here, or you can use the Z also. I'm using the M. There exists M belongs to Z. mm, Such that uh, X is greater than equal to M and less than M plus 1. Is that right, Dhruv?
Yes.
Okay. So this is the greatest integer function which uses the LUB property indirectly, or you can check the proof also. I'm not going to discuss about the proof of these examples. I will discuss only the proof of one theorem. So before that, I wanted to have some examples which will uh, help you to understand which theorems use the LUB property directly or indirectly.
Jatin,
Yes, sir.
can you scroll up the screen?
Scroll up. Yeah.
Yeah, yeah. You gave two examples. Uh, so I want to ask you whether the LUV property is true in rational numbers or not.
No.
No. Okay. So if I change my statement that for all x belongs to Q, yeah, I would
Hmm.
like to ask, is the Archimedean property true in rational numbers?
Yeah. Archimedes property is true in rational number. Yeah.
But LUB is not true. right?
Yeah,
So
yeah,
why
but
are you saying that it requires LUV
it requires.
property to prove the Archimedean property? Because it is true in rational numbers, and LUV is not true in rational numbers. The same goes for the second examples. Yeah, did you get my question?
Yeah, I get it. Your question.
Yeah. Okay. Anyway, you can think about it. You can continue, but you have to think about it. Okay.
Okay, sir. Yeah, definitely. Yeah, can you give any more examples which uses the LOB property?
Take the example Cauchy sequence is convergent.
Yeah. Kochi completeness so far. So, so do anyone of you know the statement of the Kochi completeness so far? What does it says?
Sequence xn is
Hmm.
said to be Cauchy convergent if there exists n naught belonging to natural numbers such that given any a greater than or equal to n naught and b greater than or equal to n naught, or if I yeah a and b, mod xa minus xb is less than epsilon given any epsilon.
Yeah, I think basically you are telling the definition of a Kochi sequence in R, right?
Yes,
Yeah.
and Cauchy completeness given this each and every Cauchy sequence is convergent,
Yeah.
or Cauchy completeness,
That is what I wanted to. Yeah.
where the sequences are a subset of real numbers.
Huh. So basically,
Yeah,
given
one thing.
a
Yeah, one thing. Am I audible now?
yes, sir.
I mean, epsilon you have to take earlier. You cannot say that first exist n naught and then that n naught will work for every epsilon. Without
That is
Yes.
actually mistake. Yeah, that is actually mistake by the roof. Yeah.
okay, carry on.
Yeah. So what does Cauchy completeness of R says? Given any sequence an of R, an given any sequence an in R is said to be Cauchy if and only if it is convergent. So this is the Cauchy completeness of R. Given any sequence in R said to be Cauchy if and only if it is convergent. So I hope you have already gone through the proof of this theorem also in sequence and series. Yeah. Okay. So any more example? Actually, today we have a talk on one topic that is called a nested interval theorem. Yeah. This talk will be by Gauri. So I think she will gonna prove this theorem in today's talk. So nested interval theorem also uses the concept of LUB property. So can anyone tell me what is the statement of nested interval theorem? No. Okay. So let Jn be a interval, closed interval, be a closed and bounded intervals.
Yes. Sorry. Yes, let Jn be the interval, and if we have J J2 as a subset of J1, J3 as a subset of J2, and so on and so forth.
Yeah.
The theorem states that the intersection of all of these sets, all of the Jn,
Yeah.
is singleton is
Non-empty. Yeah.
non-empty. Non-empty.
Such that
It's
Jn
not.
plus 1 is subset of Jn for all n belongs to n, then intersection Jn is non-empty. So in today's talk, so Gauri will prove this result also, and you will see that how LUB property is able to prove this. Any more example? Natural interval theorem we have, Cauchy completeness so far. So basically I have a lot, basically we have
GLB property.
yeah, it can also be proved. It is the equivalent version of the LUB property, GLB property of R. Yeah, basically we have many results in real analysis which directly or indirectly depend on LUB property. I cannot able to list all of them here. I tried to list few of them. Okay, but I want to show you one proof here so that you can able to understand how LUB property is helping us to prove the major results of real analysis. So I am going to prove a theorem in theorem continuity that is known as the intermediate value theorem. Uh, Excuse me, sir. Yeah, excuse me, sir.
Yeah. Tell Jatin.
Sir, I have at least I think it is 3:48. So how much time do I have more?
So try to finish it as soon as possible because you
Okay.
already took 20 minutes. So
Yeah, I just wanted to complete this proof. Can I?
yeah, do it.
Okay, thank you. Yeah, so can anyone tell me the statement of intermediate value theorem? No? Okay. So what does it says? It says, suppose we have a function
Sorry,
from,
sorry again. Given if a continuous function from AB to R and or even some range, the domain, given any value f of c in the domain, given any value in the domain, there exists, given any value in the codomain, the range, there exists some, okay, say f of AB is a continuous function from AB to uh, sorry, wait, yeah. Say we have FA and FB. Given
uh,
any value between FA and FB, there exists C in the domain between A and B such that f of C is equal to that value.
basically this is the standard version of intermediate value theorem. So we will not gonna prove that. I will prove the simplest one, and the later one you can able to prove this from this theorem itself. Okay, Dhruv. So the statement you said that will be become the corollary of this theorem. So this statement is like, suppose we have function from a comma b to r, we a continuous function such that we have a condition on a function such that f of a is less than 0 and less than b, then Now you see that on f of a on the interval on one end point, the function is attaining the negative sign and other and it attaining the positive sign. So do you think that the graph of a function which will cross the x-axis? Yeah,
Yes.
if you draw such graph, then you will find that uh, f will cross the x-axis, right? Then we can say then there exist c belongs to a comma b such that f of c equal to 0. Okay. So this is the statement of intermediate value theorem. So we want to prove this result. So let us try to prove this. So let me just try to draw a graph. A comma f of a, and this is b comma f of b. Yeah. So basically, I will tell you what is the strategy. What is the strategy of this proof will be. So basically, we will be going to use the LUB property. So since we are using the LUB property, we want to define a set such that we have a LUB of that particular set. So as you all know, when we proved the nested interval theorem, when we proved the Cauchy completeness of R, we have created a particular set there. Then we proved that set is non-empty and it is bounded above. Then we said that it has a least upper bound. Then we are able to prove that theorem. So similarly, we will try to do that thing here also. So how does we create a set? Let us observe one thing. Okay. So if you observe something here, like if you take any x here, if you take any x, given any x less than c, okay, you will find f of y is less than equal to 0, or we can say less than 0 because we are not including c. F of y is less than 0 for y belongs to a comma x. If you take any point behind c, you will find that f of y is always less than 0 in that interval a to c. So this is gonna be the basic element to create my set. So so all of you, do you agree that this observation is correct? Can anyone tell? Do anyone have any doubt here? Okay. So let me create a set A. I will create a set A such that even in which I will collect the element x in a comma b such that f of y is less than equal to 0 for y belongs to a comma x. So this will be my set. Using this observation, I have created a set. I am collecting all elements of a comma b such that f of y is less than equal to 0 for y belongs to a comma x. So now I want to use the LUB property on this set. Okay. So what I want to prove? I want to show A is non-empty and bounded above. Okay. So I want to show A is non-empty and bounded above. So can anyone say how will you prove it is bounded above?
We already have it in the definition.
Yeah, very nice. So what is the upper bound?
0.
0.
For f
How?
of y.
No, I'm asking for A. What is the upper bound of
For
A?
a, sorry, b.
Yeah, right. Clearly you can see that B is an upper bound, right? But how will you show A is non-empty? Do anyone of you know how will we show that this set is non-empty? So basically I have to produce element X.
We have in the definition again, no? We took
What
a
we
to
took?
be, we took f of a to be less than 0.
We took F of,
We took one element to be less than 0, one to be greater than 0.
yeah. Yeah, actually you can see that in the definition itself, the non-emptiness and the bounded above is clear, right? But let us try to prove this rigorously. Okay, so how do we do this? Now since we know, since f is continuous, f is continuous at A, right? We have the graph now. We have the graph. So at this point, we have the function which is continuous at A. Okay. Now what does it mean to say the function is continuous? That we have a given any epsilon, there exists a delta greater than 0 such that for all x belongs to c minus delta comma c plus delta intersection A, we have fx belongs to f of a minus epsilon comma f of a plus epsilon. And I think this definition is gone through all of your minds because I said orally. If you know already, then you will really appreciate this definition. So since f is continuous at A, so I can say that for epsilon equal to minus of fa by 2, there exists delta greater than 0 such that for all x belongs to, or we can write it better also, such that fx belongs to 3f of A, or I should not write directly. Let me. Fx belongs to fx belongs to, we say na, fx belongs to f of a minus epsilon comma f of a plus epsilon, right? So what is our epsilon here? Minus fa by 2. So we will take f of a minus of minus plus, that is minus fa by 2 plus, and here fa by 2 minus fa by 2. Then we have fx belongs to 3fa by 2 comma fa by 2 for all x belongs to a plus from x belongs to a comma to a plus delta. Okay. So can anyone of you give the element of this interval a to a plus delta except from a? Yeah, is anyone? Can anyone tell me the element of this interval except from a?
A plus delta by 2.
Yeah, a plus delta by 2. Yeah, you can take the average of these two terms na, at endpoints. This is the most basic we can do with these two terms, taking the average. Okay. So if you looked at this observation, f is continuous, you can find that for fx belongs to 3 f of a by 2, for all x belongs to this. Can you try to relate this thing with the definition of a set? Let me just, yeah. Can you look here? And since we know that f of a is less than 0, na? So what does it says? It says that fx belongs to, or fx, it implies fx is less than equal to 0 for x belongs to a comma a plus delta by 2. Can I do that?
Yes.
Yeah, I can do that. Since see na, f of a is less than 0 and fx belongs to that interval, and f of 3 f of a by 2 and f of a by 2 are negative numbers, so it implies f of x is less than equal to 0. Now for what value of x? For x belongs to a comma a plus delta by 2. Now see, here we have the closed interval, right? So here we will see that for x belongs to, for x is equal to a plus delta by 2, we have this condition. So therefore I can say a plus delta by 2 belongs to a. So this implies the a is non-empty.
Yeah. So Jatin, try to finish within 2 minutes.
Yeah, I cannot able to complete in 2 minutes. Yeah.
No, you have already taken 45 minutes. You are supposed to
Not for
40
45.
minutes. You started at 4:25, so it is 4:05. Yeah. Anyways, continue.
Yes. So let us, yeah. Now since we have proved the set is non-empty and bounded above, okay. So now we can say that by LUB property of R, there exists C belongs to R such that C is equal to LUB of A. So I have able to find such a C. Now I want to claim that f of C equal to 0 and C will gonna belongs to E. Sorry, A. So since we want to prove that f of C equal to 0, we will use the law of trichotomy. By law of trichotomy, we will exclude the two cases, f of C is greater than 0 and f of C less than 0. which means that we have to arrive at a contradiction in both these uh, laws, so that we can conclude f of c equal to 0. So the case 1 says, let us go to case number 1, that is f of c is greater than 0. So basically, uh, I want to say one thing here. If you have studied continuity from the Kumar sir book, you will find one exercise problem there which is related to this. Like, let me just in a separate place state the exercise. What it says? It says that let f from a comma b to r be a continuous function such that f of c is greater than 0. Okay, then there exists delta greater than 0 such that for all x belongs to c minus delta c plus delta intersection a comma b, we have f of x greater than 0. So if you have gone through this exercise problem in the Kumar sir book, you will really appreciate this proof. If you don't know about this exercise, so I would suggest you please look into the Kumar sir book about this exercise. Then you will able to understand case number 1 and case number 2. Basically, I am only using the direct result of this exercise. And proof is very simple. You can try it as an exercise problem. And similarly, we can define for f of c less than 0. Okay. So for f of c greater than 0, I can say that there exists delta greater than 0 such that for all there exists delta greater than 0 such that for all x belongs to c minus delta to c plus delta intersection a comma b. Okay, c minus delta comma c plus delta intersection a comma b, we have f of x greater than 0. Okay, f of x greater than 0. So let us keep this in mind. So now we know that since c is an upper bound, that is we say in the by LUB property, right? It is the least upper bound. So we can also say c is an upper bound. So what can I say? I can say c minus delta is not an upper bound. Now, what does it mean to say that that a number is not a upper bound for a set? It means there exists x belongs to a such that x is greater than c minus delta. Am I right? Now, if you look at carefully, where I take x is from a. Now, when x belongs to a, x belongs to a implies f of y is less than equal to 0 for y belongs to a comma x. This is the definition of a set, right? So I can say that this implies f of y is less than equal to 0 for y belongs to. Now since my x is greater than c minus delta, so I can break this interval into two parts like a to c minus delta close interval union to c minus delta to x. Okay. So basically, do you see something here? We have proved that f of y is less than equal to 0 for y belongs to this interval. But if you looked at carefully, there is one problem that we have just shown that from c minus delta to c plus delta, f of x is greater than 0. So basically it says if y belongs to this interval, f will have two values, positive as well as negative, which is not possible, right, by law of trichotomy. So it is a contradiction. Hence, this does not hold. Yeah, actually, I think I cannot able to proceed further because I already took much time. I'm really sorry about that. But it is just like the same as I did in the MTTS camp. My classmates will remember this. I when at that time I did the existence of nth root of a posterior number and I did the half proof. So this time also I did the half proof. So I would request to all of my classmates or the people here, please complete the case number 2 by yourself. Okay. So this is how we can able to use the LUB property to prove this major result. That is the infinite value theorem. I hope you get something from there. And I really enjoyed giving a talk here. So yeah, that's it from my side. Thank you.